Okay, thanks. Yeah, hi everyone. So we are still talking about this topic of solution reactions today. We have still left to talk a little bit about acid and bases and then move to the oxidation reduction reactions. And there was one join-in. I think we went until here. So let's try to do this together. We're talking about like strong bases here, sodium hydroxide and calcium hydroxide. And you have separate aqueous solutions of them with the same concentration. And you wish to neutralize an aqueous solution of HCl with that. HCl is a strong acid, as you know, right? So you have a strong acid and a strong base. And the question is, which basic solution would require more volume to neutralize the acid? Is it A, sodium hydroxide? Is it B, calcium hydroxide? Or C, more information is needed? So who thinks it's A, B, C? Yeah, it should be A, right? Because per formula unit you have less hydroxide, right? And we are talking about the same concentration. So we have the same number of formula units in the solution per volume. So if you then fix that one, then you require more volume, you double as much volume here, right? Okay. Now we want to move over from the acid base to the last part of reactions, which is the oxidation reduction reactions. In fact, this is also really important because many of the chemical reactions are redox reactions. An example is combustion reaction. We have here methane gas, CH4, and we can let this react with oxygen. Then what will happen is we will form carbon dioxide and water and a lot of energy, which is key to energy, but also key to our body. We have also combustion reactions happening in there. So the question is like these kind of reactions. Well, this is another example. Sodium reacts with chlorine gas to form sodium chloride. So the question is, how can we understand these reactions? What is special about them, right? And the idea about these reactions is that you have usually some kind of imaginary charges on these atoms, which tell you how much these atoms want the electrons. So if you remember, remember the water molecule, right? The water molecule, the oxygen has a tendency to get these electrons, while the protons or the hydrogen will lose them to become protons, right? So this is what we called, or what we call now is partial charges. And one problem we had here is that we couldn't really quantify these, right? So we could say, well, oxygen kind of prefers to get electrons because oxygen wants to get 2 electrons to become noble. But we couldn't really say that how many electrons it actually gets. It doesn't get 2, that's for sure, because if it would get 2, it would just dissociate and form an ionic bond, right? But something like between 0 and -2, right? And for the protons, it should be the inverse so that the neutrality is satisfied. So we want some way to kind of quantify how many electrons these atoms have. Because if we can do this, then we can realize that many reactions, chemical reactions, involve electrons moving from one atom to the other, and that is exactly what we call oxidation and reduction. Okay, so the oxygen in this case has a higher electron affinity. that's why we assigned it a partial negative charge. And the question will be, can we give it an actual number? And the solution to this is the so-called oxidation number, oxidation state. For ionic compounds, we will simply assign the charges of the ions. So oxidation numbers are equal to the charges of the ions if we have ions. That's pretty straightforward. And it makes sense that we define it like that, right? It should somehow satisfy that limit. So if we have sodium chloride, the oxidation number of sodium would be 1 and chloride would be -1. We usually use these Roman letters for that. Or if we have like calcium hydroxide, this would be 2 and this would be -1. So the charges here in this case equal the oxidation numbers. Yeah, so these are the charges and the oxidation numbers are kind of equal. And the sum of those oxidation numbers has to always add up to 0 as well, similar to the charge. So for ions, this is pretty straightforward. But when it comes to molecules, this is a bit more tricky. So here, they define some rules that we can use in general. And the rule is like this. Well, personally, I don't like the rules, but I have to always think in my head what I can explain you with your current knowledge. So the idea is like this. So if hydrogen makes some molecule, the hydrogen will almost always lose its electrons to the oxygen, because oxygen has a higher electron affinity than hydrogen. So we can kind of draw it like this. The electrons all go to the oxygen. And then we are left with a simple proton. So we can write this one as an H, with the number 1 here. And the oxygen has gotten 2 more electrons, so we write it as a -2, right? So in this case, you can see that the oxidation number is simply the same as what we would get if it would fully dissociate into the ions, right? But that's not always the case. That's a case in this particular situation. It is like that. But sometimes it's more complicated to get these oxidation numbers. But the general idea is we divide the electrons based on the electron affinity. Yeah. So another example, if I draw the methane here, then carbon has a higher tendency to get the electrons, and hydrogen still wants to lose the electrons. How many electrons does the carbon want to get? 4, right, to become noble. So it can, right, it can get all these 4 electrons. So it would become +4 is the oxidation, -4 is it has 4 extra electrons, and all the hydrogen will be +1, right? So this is the oxidation number. So you can kind of see it as a kind of drastic version of electron sharing, right? Suppose that electron affinity will be so strong that it will just completely transfer all these electrons. This is not what happens in reality. In reality, the proton will not completely give away its electrons, right? If it would, then it would just become C -4 plus 4H+. But this doesn't happen, right, in reality, because we are talking about covalent bonds. And covalent bonds mean always that the electrons are shared. So the oxidation numbers are kind of a way to quantify the charge, but they are not giving a physically reasonable charge. So they are in the extreme limit that all the electrons would transfer. Yeah? But that can be actually helpful for us in many cases to understand chemical reactions. So some more examples here. Of course, if we have only the atoms of the elements, then always the oxidation number would be 0. For ions, it's exactly equal to the charge. For fluorine, for the halogens, they usually like to lose one electrons, as you know, right? The halogenides, fluorine, chlorine, bromide, iodine, they will always lose one electron. Hydrogen always, get one electron, not lose, get one electron. Hydrogen wants to lose one electron. Alkali cations want to lose one electron, right? Always want to become noble. So if you know the rules about becoming noble, then that's fine, right? Then you can assign the oxidation numbers. So as I said, for this simple system, it's very easy to determine the oxidation number. Simply go by the affinity to accept or release electrons, and you have the oxidation numbers. Yeah, things can become a bit more complicated if you have like molecules. Let's say you have something like ethanol. And you need to think a little bit about it, because now you have a carbon and an oxygen. You need to think what has a higher affinity to get the electrons, and then you can assign again the electrons and get the oxidation numbers, right? But this example we will not do this here. We will do very simple examples for now. But in principle, if it becomes more complicated like this, you just need to go over every single bond and need to decide which atom gets the electrons, and then you have the oxidation number, right? So oxidation number in general just means that assign the electrons to the more electron affine element in a bond. Okay. Okay. Now we do some examples here. We have CO2 and NO3 minus. So for oxygen, we already have the rule that oxygen has a high electron affinity, so it will commonly always like accept the electrons. So we will set this to -2. And then the carbon you can simply determine by neutrality of the molecule. So if these oxygens are -2 and -2, the carbon has to be +4, right? To neutralize the charge. So we have +4 for carbon and -2 for the oxygens. Okay, and just to check, you can see if the neutrality is satisfied, and it is. +4 -4 is 0. And the second example was NO3 minus. Again, oxygen is -2. To get the nitrogen oxidation state, we have to then make sure, because the final charge has to be -1. So the sum of all the oxidation numbers has to be -1, which means that nitrogen has to be +5, right? 5 minus 6 is -1. Okay. Okay, some more exercises for you to do maybe at home. So idea is always you start from the elements where you already know the oxidation number. So for example, oxygen is -2, potassium is +1, right? Always potassium likes to lose one electron. Manganese, we don't know it. Manganese is a transition metal, and we know it can be many different oxidation states. So again, we take like +1, -8, and then what is remaining is -7, so manganese must be +7, right? So that's the idea how we can always determine the oxidation numbers. Okay. And now once we know these oxidation numbers, then we can understand what happens during oxidation reduction reactions That's simply a transfer of electrons, so it means an increase of the oxidation number of one of the element and a decrease of the other element. Okay? So oxidation means that the oxidation state increases, which means that we lose electrons. And reduction means that we get the electrons and decrease the oxidation state. When we have something that can accept electrons, we call this an oxidizing agent because it removes electrons from another partner, so it oxidizes the partner, right? When we reduce something else by donating the electrons, we call this a reducing agent. Yeah. So oxygen gas, do you think it's oxidizing agent or reducing agent? Oxygen gas. So oxygen gas is oxidizing agent because it has a tendency to get electrons and become O2 minus, right? Which means that it has a tendency to pull away electrons from the partner, meaning oxidize the partner, right? Okay. So oxidized means that an oxidized species has lost electrons, right? From M to M plus, we lost the electrons, and these electrons move to the partner to reduce the partner, right? Okay, this is, if it becomes oxidized, it means it's a reducing agent. If it becomes reduced, it means it's an oxidizing agent because it can oxidize the partner. Yeah? Okay, so let's do some example. This is an example from metallurgy, process of producing a metal from its ore, and which always involves these redox reactions. So we have here an example of galena, which is lead sulfide. And this is the principal lead-containing ore. And the first step in converting it is to oxidize it with oxygen gas to form lead oxide and sulfur oxide. Okay. So we can do some analysis of the oxidation numbers to understand what is oxidized here and what is reduced. Right? I just told you oxygen is an oxidizing agent, so we will probably expect that the oxidation number here should somewhat increase, right? So let's see what happens here. Okay, so but there's another reaction we will look into after that, which is the further processing of the lead oxide to lead. But let's go step by step. So for the first reaction, we determine the oxidation numbers. Sulfur is the same group as oxygen, right? It likes to get 2 electrons. It's -2. Lead then must be +2, right? So we don't even need to memorize lead. Lead must be +2 then. Oxygen is 0 because it's the element. And then here we have lead oxide. Oxide is still -2. Lead is +2 still. So maybe you thought when you looked at the reaction first, maybe lead should be oxidized, but apparently it's not. Lead has the same oxidation number, so nothing happened to lead. Lead was just a spectator, right? But what happened to the sulfide here? So sulfide has -2 before, and now it has +4. Okay, so sulfur has been actually oxidized, and the oxygen here has to be -2 because oxygen is always -2. Yeah. So now you could ask, why is not sulfur -2? Why is oxygen -2? Well, that's the reason of the electron affinity. So it turns out that oxygen likes to get the electrons more than sulfur. Yeah. So later we will talk, I think, about electronegativity, which will help us to rationalize, to quantify the tendency of elements to get the electrons. And it turns out that if these elements are more in the top of the periodic table, they have usually a much stronger driving force to get electrons. That's related to the fact that once you go along these lines, along the rows of the table, then you add more and more electrons, right? And as you add more electrons, all these electrons compete for the nuclear charge. So they like to attract to the core of the atom. And so it turns out that this will decay. I mean, this will make the tendency to get more electrons much weaker than for the small atoms. It was just a physical side story. So oxygen will be -2. And if it's -2 times 2, that means the sulfur should be +4, right? So sulfur is oxidized. Oxygen, what happens to oxygen? Oxygen is reduced from 0 to -2. As expected, oxygen is our oxidizing agent here. Okay? How about the second reaction? So here we have lead oxide reacting with carbon monoxide to form lead and carbon dioxide. Again, we do the oxidation states. Oxygen is always -2. Lead must be then +2. Oxygen always -2. Carbon must be then +2. Lead element is 0, -2 and 4. And now we can simply look what element is oxidized here. So how about carbon? Carbon is +2 before, +4 after that, right? Carbon is oxidized. Carbon is losing electrons in this reaction. And what element is gaining the electrons? So we can look here, what happens to the lead? Lead is decreasing oxidation number. So the electrons from the carbon move over to the lead. Yeah, so we have an electron transfer from the carbon to the lead. Okay, so this is what is a redox reaction. Redox reaction is a transfer of electron from one atom to the other, which actually drives the reaction. It drives the reaction forward. Okay. So let's do some joining for this. We have a reaction of sodium bromide with chlorine gas to form sodium chloride and bromine. What are the appropriate half reactions? And ox means here oxidation and re means reduction. Okay, you can read this by yourself and then give me your answer. Okay, so how about the first one? Who thinks that this is right? Okay, so why is this not right? Why is this not correct? Someone explain it. That's right. Oxidation loses electrons, but here the chloride is actually gaining electrons, right? So the oxidation number actually decreases, which is called reduction, right? So that's not right. How about the second one? Who thinks that this is right? Okay, so here we have bromide here, and bromide is, the oxidation number is increasing, right? How about chlorine gas? Chlorine gas oxidation number is decreasing, that's the reduction. So it should be right? Should be the right answer. While the others I think are clear, we cannot get B or a plus, right? And well, the last one, the sodium, shouldn't do anything because we have sodium in the initial and the final state. So B would be the right answer. How many of the following are oxidation reduction reactions? Let's do that again in the other way. We will just go one by one and I'll ask you if it's oxidation reduction. Let's look at the first one. Is it oxidation reduction reaction? Is it a redox reaction? Who thinks that this is a redox reaction? And let me ask why the others think it's not a redox reaction. What happens to the oxidation numbers here? What are the oxidation numbers here of chloride? 0. And here? -1. Right? So here's -1 and 0. How about phosphorus? Plus, not 1, 3, right? Plus 3. Okay, so let's write this down. Here, -1 and 0. How about the final state? What is the chloride? Still -1, right? Halogenides always want to get 1 electron. So this has to be 5, right? 5. Oxidation number 5. So what happened is that the phosphorus actually lost 2 electrons, right? And at the same time, the chlorine gas here, it actually gained these 2 electrons. So it's a redox reaction. Yeah? One atom is gaining electron, the other one is losing it. It's a redox reaction. How about the second case? Who thinks this is a redox reaction? What's going on today with you guys? Too tired? We need more hands. Redox reaction. Redox reaction means oxidation number, one of the atoms increases, the other one decreases. So think about the oxidation numbers here. Okay, so who thinks this is redox reaction? Couple of more. So copper is 0. What is copper here? 2, right? This is nitrate anion. It's -1. So it's a copper 0 to copper 2. So this is getting oxidized. At the same time, the silver is going from 1 to 0. It's getting reduced. Redox reaction. Yes. How about the third one? Who thinks it's a redox reaction? No one? So carbon, or let's start with oxygen. Oxygen is always -2 in this case. We don't have any oxygen gas, right? And oxygen otherwise in the compounds is always -2 usually. So oxygen definitely doesn't get reduced or oxidized. Hydrogen is always +1 if we don't form hydrogen gas. So again, this doesn't participate. Lithium is +1 here, it's +1 here, right? It's carbonate is -2, and this is 2 cations, so it's balanced, it's still lithium plus. So lithium is also not getting oxidized or reduced. And then the carbon is left, carbon is 4 here and 4 here, so nothing happens with the oxidation numbers. This is not a redox reaction. And the last one we can do quickly, iron is 2 and 2 here, sodium is 1 and 1 here, chlorine is -1, -1, oxygen -2, hydrogen 1, all of them stay untouched. It's not a redox reaction. Which of the following is not an oxidation reduction reaction? A precipitation reaction. B, a reaction in which a metal reacts with a non-metal. C, a combustion reaction. D, a reaction of a metal with an acid. E, all of them are oxidation reduction reactions. Okay, who thinks A, B, C, D, E? Okay, I give you a bit of time. No answer is not good. At least I need a couple of ones. What is a precipitation reaction? Precipitation reaction, right? For example, Na plus Cl minus. Does the oxidation state change? No, always plus or minus. Okay, so definitely this is not an oxidation reduction reaction, right? How about B, a reaction in which a metal reacts with a non-metal? Yeah, so typically the metals want to get rid of electrons, right? So if there's a non-metal which usually can get the electrons, like oxygen or sulfur, fluoride, then this will make a reaction usually. So this is a typical example of an oxidation reduction reaction, where the metal gives away the electrons. Combustion reaction. Is it, who thinks that this is not oxidation reduction? Who thinks that it is oxidation reduction reaction? Yeah, couple of hands. I just explained it like 10 minutes ago, but maybe I should talk in Korean. But I don't know all these terms, that's the problem. I don't know what is combustion in Korean. That's my problem. I can speak some Korean, but... Okay, reaction of a metal with an acid. Who thinks that this would be an example of oxidation reduction reaction? Yeah, this is also an example. So the metal will become oxidized usually in the acid, and then we can form, something will be reduced in the acid. For example, the protons can be reduced to hydrogen. So we have a metal plus protons, and this can form like cations and a hydrogen gas. Okay, in this case 2 plus. Right, so this is one example what can happen. So this is how an acid can actually eventually dissolve the metal. It can form hydrogen gas. The protons get reduced, metal gets oxidized. Okay, what are the oxidation numbers of carbon in CO2 and CO3 to minus? about A, B, C, D, E. Oh, okay, that looks better. More hands is always good. Yeah, that is correct. Classify the following unbalanced reaction. Magnesium reacts with HCl to magnesium chloride and H2. So essentially this is the combination of this reaction which I draw here and a precipitation reaction, right? So then the metal can react again with chloride to form a metal chloride. So this would be the precipitation reaction and this would be the actual redox reaction, right? So they combine this here into one reaction. Which means that essentially we have here two things. We have an oxidation reduction reaction as well as a precipitation reaction, right? So it would be kind of the combination of both. Even though in the solutions they write as oxidation reduction, but it's actually the combination of both. Yeah. Precipitation is also involved. Each of the following results in a chemical reaction. Which of these is not an oxidation reduction reaction? A, methane gas is burned in air. B, iodine crystals are added to an aqueous solution of silver nitrate. And a piece of silver metal is placed in an aqueous solution of copper 2 nitrate. Okay, methane gas is burned in air. Who thinks that this is not oxidation reduction reaction? Okay, so methane gas is burned in air. So how does the reaction look like? CH4 reacts with air. What happens during that reaction? Well, this is just a combustion reaction, right? So we will form CO2 and water. In any combustion reaction, we will always form CO2 and water, right? Now this is not balanced yet, but we can do this. So we have one carbon. We have here 3 oxygen. We can do 2 here. We have 4 oxygen. And we can do 2 here. Right now we have 4 hydrogen and we have 4 oxygen on both sides. So what is the oxidation number? Carbon is here -4, hydrogen is 1, oxygen is 0, 4, -2, 1, -2. Okay. So is it oxidation reduction reaction? It is, right? Carbon is getting oxidized, oxygen is getting reduced. Okay. B, iodine crystals are added to an aqueous solution of silver nitrate. Iodine crystals are added to an aqueous solution of silver nitrate. Think about what kind of reaction will happen here. So iodine likes to get electrons, right? Likes to become negative. So we will probably form some kind of I minus. At the same time, something will become oxidized. Actually, what is becoming oxidized is a good question. Silver must become oxidized, I guess. But silver is usually in oxidation state +1, so I'm not sure what they mean here. I'll look this one up. What happens during this reaction? I'm actually also not quite sure what happens during. I think it's oxidation reduction reaction, but I'm not really sure what is becoming oxidized. Probably it's silver, but silver is usually always +1. I will look this one up. I will tell you next time. Maybe silver is getting oxidized. Okay, next one. A piece of silver metal is placed in aqueous solution of copper 2 nitride. And reaction happens, and silver can become oxidized, right? And the copper becomes reduced. So you could form like silver plus and copper. So then you have a redox reaction, right? Nitrate is just a spectator, it's not really doing anything. Of course, you need to kind of balance the electrons. So here you have 2 electrons. It gives 2 electrons to the copper, right? Okay, this would be one example here. And then another one. Chlorine gas is bubbled through an aqueous solution of sodium bromide. So this one we had already before. I think chlorine becomes chloride and bromide becomes bromine. So it's also redox reaction. And the last one, aqueous solution of lead nitrate and sodium iodide are mixed together. This is just the precipitation reaction, right? Where we have cation of the one salt reacting with the anion of the other one to form precipitate. Yeah? So E is the only one which is not redox reaction. Yeah, actually this reaction I think is also not a good example because copper likes to be oxidized compared to silver, right?
Cannot be reacted.
Sorry?
You say it cannot be reacted.
No, it cannot react in this way. It will react in that way actually. So I don't know why they said everything is a reaction. This is actually, it will not happen like that. So copper of course has a higher tendency to be oxidized than silver, right? Otherwise, why would you wear silver rings? You can wear copper rings, right? On your hands. Okay, one more. Which of the following compounds contains nitrogen with the highest oxidation number? Okay, who thinks it's A, B, C, D, E? So B is correct. And the nice thing about this is now you can do chemistry, right? Now you know how to do chemistry. Once you know the oxidation numbers, you can actually write down chemical reactions, right? If you have an oxidizing agent, you can start from nitrogen, and you can move towards oxidation number 2. Well, actually, you can start here. It's -3, 0, 2, 3, 4, right? So you can actually do some chemical reactions. You can sequentially oxidize the nitrogen, and you can get many different chemicals out, right? So if you choose the oxidizing reagent correctly, then you can get all these chemicals out from ammonia. And the other way around is actually much more interesting. How can you get ammonia from nitrogen? Why is that interesting? Because ammonia is the basic component of all the fertilizers in the world. So without that, we would all not be here today, because the population of the world is only increased because of the invention of a chemical process to make ammonium salt from a reduction of nitrogen. So that's one example of an oxidation reduction reaction. So once you know how to control, how to stop at some of these chemicals, that will be important, right? Let's say you want to oxidize ammonia, but you want to get NO, you don't want to get NO2. Then you need to have an oxidizer which is not too strong, right? Which doesn't fully oxidize everything to NO2. So by choosing the oxidizing and reducing agent, you can do all kind of chemistry that you want to do. Okay, and in order to understand this a little bit better, it helps usually to write down half reactions. So half reactions are kind of splitting the reaction into an oxidation and a reduction. Because eventually what happens here is that always one of the reactants is losing electrons, the other one is getting the electrons, right? So you can write down the electrons explicitly to understand this a little bit better. So for example, you can write down here methane. Methane is somehow reacting to CO2, right? That's what we know. And the oxidation number goes from -4 to +4. So how many electrons did we lose here? We lost from -4 to +4, so it's 4 electrons, right? And so 8 electrons, right? 8 electrons. So this would be the oxidation reaction. And then reduction reaction. This is O2 reacting to H2O. And here we are going from 0 to -2, and we have to do this one. Sorry, 2. Yeah, this would be correct. Okay, let me do this. Do this one first. This. So now we go from 0 to -2, and we need to add 4 electrons because we have 2 oxygen atoms. Now the electrons and the oxidation numbers are balanced, but as you can see we have a bit other problem because our numbers of atoms are completely unbalanced, right? So if we want to make sense of these half reactions, we should add some other elements to the reaction equation to balance this one. Also, yeah, okay. So first of all, we can start adding like water to the reaction. And we can also start adding some other species that we typically have in the solution, such as protons and hydroxide ions. So what we typically do is we first add protons and hydroxide ions, because we typically have them in the solution. Either we have an acidic or an alkaline solution. Let's say we have an acidic solution for now, and we would add here 8 protons. Why 8? Because we have 8 electrons, right? And the charge should be balanced. Here we have a neutral side, so this side should be also neutral, right? And then we can do the same thing here. We add 4 protons here. And now we only have to balance the number of atoms. So here we have 4 hydrogen, here we have 8. So we can just add some water here. Water we also always have present. Now we have 2 oxygen here, 2 oxygen here. We have 8 hydrogen here, 8 hydrogen here. So this is a fully valid half reaction. And here we can do the same thing. We have 4 hydrogen here, 2 oxygen. It's already balanced, right? So now what we need to do is we need to make sure that the electrons are the same. So we would typically then just multiply this with 2. And we have 2 O2 plus 8 electrons plus 8 protons and 2 water. So this would be the oxidation reaction, this is the reduction. And what you can see is if you add this one here plus this one, 1 plus 2, and you end up with exactly that equation that we had before, right? So the half reaction is useful to derive and balance the final equation. So the process here is that you first write down the species that are oxidized and reduced. Then you determine the oxidation numbers and the electrons. Then you balance the charges, and then you balance the atoms. Eventually you multiply with 2 to get the final equation, right? Okay, so here they write this strategy. So you write down a separate equation for oxidation and reduction. You balance, so they balance the elements first. Personally, I recommend you to do the charges first and then the atoms. So I would probably recommend you to oxidation numbers first, then the electrons, then the charges, and then the other atoms. They have a bit different, they have exactly the inverse. In the end, both should somehow work, but I just like this strategy a bit more. You can do whatever you need, whatever is good for you. And then, if necessary, multiply the half reactions with an integer so that the same number of electrons is there. And then you add them up. And you can see there are 8 electrons here and 8 electrons here, so they cancel. There are 8 protons here, 8 protons here, so they cancel. There's 2 water here and 4 water here. So 2 cancels and 2 water is left. So we get exactly this equation, right? So this is the final step, and then you can one more time check everything is correct. Okay, so why this is useful? Well, because it helps you to usually balance the equations, and also there's something which we call electrochemistry, where we can actually separate the half reactions. We can do one reaction on one side, the other side. It's very important for any electrochemical applications such as batteries or others. So it's quite useful for us, and we will practice this more on Thursday. Okay? Thank you for your attention.